Hello, my name is John Hedengren, and I'm going to be presenting some information on a new flow assurance system with high-speed subsea fiber optic monitoring of pressure and temperature. My co-authors on this are David Brower and Conrad Wilson from Astro Technology, and also Jeff High and Carl Witherow from Ocean Flow International. A little bit about Astro Technology. Astro Technology started in the space rocket motor monitoring industry, and then moved on to things like the Robonaut hand, the astronaut robot, and adding fiber optics to be able to have tactile feedback. Right now, Astro Technology focuses on subsea fields, pipelines and risers, and LNG facilities. And engineering capabilities include the items that are mentioned down here. A couple previous instrumentation jobs on flow lines and on risers. There you can see the strakes and the instrumentation clamps, and there you can see as well an umbilical cable that reaches the sensors. So what is the need for better subsea instrumentation? We want to detect early warning signs, be able to give operators early indication that a problem is developing. We want to also automate the monitoring of critical systems, be able to give feedback when necessary, and also track pressure, temperature, strain, and flow. We want to give critical data to key decision makers, not just raw data. Be able to analyze that and give them decision information, and also eliminate production downtime, prevent asset damage and pipeline leaks, and reduce safety and environmental risks. Some of the new developments with this presentation are high-speed pressure and temperature data. In this work, we went up to 100 Hertz, which we had not done previously. Also, I'm going to describe some sensing array configurations for flow assurance to be able to detect pressure and temperature from fiber optic sensors. Also, we did some work on sensor calibration, and then demonstrate the long service life. I'll give a case study that just shows the longevity of these sensors. Okay, here's the performance with sensor location. We had 3 sensor stations installed on each of these. This is a flow line end termination or an inline sled. And so this is without the steel structure right here, but with the steel structure that sits on the seafloor, and then the well fluids come in at that location and then leave here. Here's the configuration of the well. Here's well number 1. And then well number 2. And so the production fluid starts here, it flows along this pipeline, and there's a large gap between these, and then you have the well fluid that enters here, and the total length of this is about 18 miles, and this is about halfway. The fluids then go to a production riser where they're processed and delivered to markets. Here is the photo of the sensing stations as they're being installed. There you can see station 1, station 2, and station 3, and then again on the diagram. In order to be able to get pressure, we put sensors in the hoop direction, or give a hoop strain. So as the pipe expands or contracts with pressure, that gives us very precise readings of pressure. We also have axial strain. We put a sensor in the axial direction, and that gives us bending and vibration. We also have a diagonal strain, and that will give us torsion, although we didn't need to install that for this application. And then one that isn't attached to the pipe is going to be for temperature, because there's a temperature effect, a shift in wavelength due to the temperature. So this is an overview of how fiber Bragg gratings detect strain. There is a spectrum source of light that is sent out from a fiber optic interrogator. There are gratings that are placed into the line before they're installed, and a portion of that wavelength is then reflected back, while the other portion continues on. So this is the portion that was reflected back, and that goes back as a peak that then shifts to the right or to the left as the strain changes and changes the distance between those gratings. And then on the next one, there might be another portion that's taken out and reflected back, and so on. So using this method, you can have up to 100 sensors placed on a single fiber optic strand. We use these formulas to convert the microstrain, the change in wavelength, into microstrain, and then also the change in wavelength into temperature and into pressure. And more details on this are given in the paper. Here's a cutaway view of how the sensors were installed. First, the diagram here. We have an axial strain placed in the axial along the direction of the pipe, a hoop strain that's placed in the hoop direction, and also a temperature sensor. And then this is the ruggedized version of that with the polyurethane coating, and you can see this cable that comes out, and then this is a connector, an ODI connector that then connects to the umbilical and then back to the topside platform. Here's a photo of that. There you can see the connector and the cable that comes down into this sensing station. So everything on this is ruggedized and it's ready for deployment and painting. We also did some pre-deployment tests. Here's our fiber optic interrogator that we then plugged into the computer. You can see some of the wavelengths right here. And so we did some of the calibration beforehand, as this was a dry install. Here are some of the calibration pressure testing on a different test article, where we went from essentially zero, almost zero, up to 2000 psig. And the blue line is the conventional pressure gauge, and then the red X's here are what the fiber optic sensors were telling us were the pressures. So fairly good agreement there. A little bit out here, it may have been because of the conventional gauge, not the fiber optic. Here's also the temperature readings. We expect that the temperature and the subsea fields, typical sensors on this system are going to range between about 38 degrees Fahrenheit all the way up to about 100 degrees Fahrenheit. And so this approximately covers the range that we're interested in, and there you can see some of the calibration data for temperature. Now another paper that also talk about is this OME 77117, where NASA developed friction clamps and then tested those under tension and compression. And then another style of this is also an adhesive clamp that can be installed by divers. So both of these are options. In this case, it was prefabricated, so these are not post-installed designs, but those are also available. This is an overview of how this fit into the overall system architecture. Here's your fiber optic interrogator with your fiber optic sensors. The data is then transmitted to a database and analytics, where a lot of the analysis is done. That information is given to an operator and to a supervisor. It's also sent via a Modbus connection to the distributed control system. In this case, this is a Delta V control system. Here's the installed performance. I'm going to go over each of these in just a little bit more detail, but overall you can see that there was an attempted startup right here on this is the first wellhead, and this is our second wellhead here, where they attempted to start up on the first one. There were some issues, and so they shut it down, but you can see some of the lingering temperature effects right here. and they went for a startup on well 2 instead. So you can see the temperature rise, you can see the flow rate increase. And if we look a little bit closer at this first one, we'll see, the well fluids are coming, from the well into this line here, and then out toward the platform and toward the second well where they're going to be mixed. Now there was a blind here, meaning that was cut off from the, actually it was a little bit before that. And so the only way for heat to transfer that way is for this whole structure to heat up and for heat to transfer. And you'll see over the course of about a day and a half that temperature rose at T3. The other ones you see right here that there's an attempted startup and then it shut down, so there were some warm fluids in here and it eventually cooled off. You can see the MPM, the multi-phase meters, what we're comparing to. That one cooled down much faster because there's a multi-phase meter that is sensing the fluid itself versus these sensors that are located on the FLET are measuring essentially the not just the fluid but the outside of the pipe. Okay, but there's excellent agreement between those temperatures. Let's go on and look at the startup temperature tracking on the second well. So this one started up at this location right here. And one of the things that we immediately see is that this third temperature was received some heat by conduction. But then when it starts up, you have cold fluid here that needs to be this slug of cold fluid that's transferred out over the course of a half a day. And then as that fluid is heated up that pipeline and the warm fluid starts to come through as it's flushed out the cold fluid, then that mixes with the well number 2 fluid. Okay, and this is well number 1 fluid, and then this is the mixture of the two. So T1 and T2 are located right here, and that's the mixture of the two fluids as those two streams converge. So why is this important? Well, we need to be able to monitor temperature for hydrate potential, and so before and after this junction point is very critical, especially during complex startup sequences like we've seen here, where it's very difficult to otherwise manage the temperatures and pressures. Okay, just pointing some of these sensors out on the plot. Okay, one of the things that we're continuing to work on is, now that we have this raw data, is to turn that into actionable information. And we can do that either with empirical model identification, through the use of things like neural networks, or hybrid modeling that might be able to extrapolate better. This is just a demonstration problem that shows the extrapolation of fitting a sine wave. And instead we said, well, that looks like a trigonometric function, so we're going to use a cosine instead, and it's able to fit that with some partial information that we give it about the structure of a problem. Now what we want to do is turn that into actionable information, so look for early warning signs of problems such as hydrate formation or other flow assurance issues. Another future work item is something called model predictive control, where we're going to take these measurements and our predictive model and be able to have it manage startup sequences. For example, ramping up the production typically takes over the course of a couple hours, and the operator is always watching certain constraints. There's an opportunity here to use these predictive models to be able to manage the startup sequence with an automation package that can continuously monitor the constraints and try to emulate the best operators. A little bit of information about long-term service life potential of these fiber optic sensors. This was a project that was initiated in 2007 and then really began in 2008. A little bit more information about the Devil's Tower platform and the Bass Light flow line. It's located in the Atwater Valley Block 426. It used an 8-inch diameter flow line, which was 90 kilometers in length, or about 56 miles, and it produced about 130 million cubic feet per day. It was in water depth about 1.25 miles down, and it commenced operation in February 2008. It was decommissioned with assistance from Astro to help them locate a hydrate plug. So one of the things that we had done earlier is installed this, but at the time when they were decommissioning in 2016, they needed some help locating the hydrate plug, and so we were able to go back to the platform and assess the sensors at the end of the service life of the flow line, and all of the sensors were fully functioning. So that was from 2008 to 2016, an 8-year time span where there was no degradation of the sensors. So new developments in this presentation, we have high-speed sensing of temperature and pressure. We have flow assurance at key flow line locations, in situ sensor calibration, and then also fiber optic sensors exceeded the service life of a Deepwater flow line, in this case about 8 years. So it shows that the ruggedization and the long-term service life. I'd just like to mention this was made possible by the Clear Gulf study, which is a cooperation between NASA through the Space Act Agreement and Astro Technology and oil and gas partners through the Clear Gulf Joint Industry Project. One of the things I want to do in this next part is just go over some of the information about the Clear Gulf Joint Industry Project. And I'll talk about some of the testing of this friction-based clamp. So this friction-based clamp, there were 3 different generations of the design, and I'll talk just briefly about the first generation and then the other 2 generations, and also why we want to do a friction-based clamp design. Again, here's some previous installations on risers, TLPs, and flow lines, and the one that we're focusing on here is this friction clamp. And let me change the color of the marking because I think blue is not going to work too well for this one. Okay, so there is the friction clamp, and this can be ROV'd installed. So the last presentation I showed was pre-installing it on dry equipment, and the friction clamp can be installed subsea. So here is a basic procedure for developing this clamp, doing a feasibility evaluation, the conceptual designs and drawings, and then iterating on this prototype and testing and then refining the design. So the final design is going to be this Mark III or version 3. First of all, the version 1, this was a carbide coating for friction with a hinge here, and it was clamping shut with the aid of 5 bolts. Here is the 8-inch test article and a 4-inch test article, and these tests were conducted at NASA Johnson Space Center. Some of the results from the first prototype is that the carbide friction coating was very effective. There was no slippage, but one of the big drawbacks of this are that there's 50% of the needed strain as observed by the conventional strain gauges. This is the version 2 design, where instead of having a solid clamp here, you just have 2 bands. They're located parallel to each other, and these sensors are then cross the divide between these 2 bands. Here's a photo of that, where there's spot welding of these sensors at these 4 locations. One of the reasons why the first generation didn't work is due to the effect of the carbide friction coating that did not allow the sensors that were placed a certain degree away from the bolting action to be able to be coupled with the pipe. In some cases, there's as low as 10% observed. If you were 90 degrees away, it predicts with that friction factor, okay, this is increasing friction factor as you go down, that you would have only 10% of the observed strain that you would expect. So if there's no friction, then you would have 100% everywhere, but you need the friction in order to be able to have the coupling of the sensor to the test article. Here's the Mark 1 to Mark 2 design. Here you can see Belleville springs that hold those in place. Now the ruggedized version won't necessarily include those. There'll be some stainless steel and other components that are good for deep water applications. But this one helped to get the bolts tensioned and maintain their tension even under extreme deformations of the pipe. Here's some of the workers putting the clamp in place. And this was a 24-inch diameter, 0.5-inch thickness test pipe that came from a section of a riser. So it represents a riser quite well. And this was tested in tension and compression. Here you can see the test article for the tension and the test article for the compression. And there were going to be 10 strokes applied in each, up to about 1,000 Kipps, which would be about 900 microstrain. Here you can see 6 cycles of the tension test, and this is the 9 cycles of the compression test. Now there's excellent agreement here. You can see a little bit of the just how they were needing to do the full test. They had to do that in 2 phases, going up and down and then resetting the 0 value. And so there's excellent agreement throughout with conventional strain gauges and the fiber optic sensors. On the compression tests, it was another matter altogether. We were expecting somewhere around 900 microstrain, but all the sensors were off from that. And in fact, they didn't agree with each other. This may have been due to some damage of the rosette connection of the conventional strain gauges. And these were high right here. I'll mention that in a previous slide why we think those were high. Okay, so they were about 7 to 16% higher than expected, depending on the sensor type for the fiber optic sensors. Now, one of the reasons for that may have been just due to where these were spot welded in place. As you're going under extreme compression, there's the potential for buckling, okay, where it could move out or in, and that would be an additive effect toward the compression test. Okay, so Mark III is going to be the new generation. Now this one is a ruggedized version of Mark II, and then also incorporates many of the learnings that took place from the compression and tension tests. There you can see it open, where the ROV can install it around the pipe, and then closed, and it would be bolted down. So future work is repeat testing of the Mark II prototype for compression tests, just to verify that the fiber optic sensors work well under compression, but without that bowing that we think took place. And then development of the Mark III design that's going to incorporate ruggedization, ROV installation, handles, and also the improved carbide coating application technique. Again, this is a joint venture between NASA and the Clear Gulf Joint Industry Project through the Space Act Agreement. And thanks for your time and attention. Okay, so that's it for these 2 presentations. Please let me know, or you can email questions if you have any. Thanks.